Dear colleagues, let me present the main results of scientific research on the topic gas consumption forecasting using machine learning methods and taking into account climatic factors. The growing demand for energy consumption is the reason for the development of means and methods for optimizing and controlling the use of these natural resources, and natural gas consumption is no exception. In this context, the subject of processing and forecasting natural gas consumption attracts significant interest from the researchers who are interested in developing innovative solutions to improve obtained results. New mathematical models and gas consumption processing and forecasting methods using machine learning techniques are of particular interest. Many researchers are engaged in the development of gas consumption forecasting methods. For example, in literature source number 3, gas consumption forecasting was proposed using hybrid neural network with the approach of artificial B-counts. In literature source number 5, 4 different forecasting models using a block structure and combining its elements to create hybrid models were developed. In source number 7, short-term forecasting for the next day was investigated. In literature source number 10, the use of deep neural networks for short-term gas consumption forecasting was proposed. Our paper examines a method for forecasting gas consumption process based on the application of an additive mathematical model. One of the components of this model is a cyclic random process. The forecast is constructed using machine learning methods, specifically gradient boosting and decision trees. Briefly about main results of our research. The model of the cyclic random process of gas consumption is presented in the form of an additive model. Here we have the sum of 3 components: cyclic component, trend function, and stochastic function reminder. Expression number 1. In practice, we have to deal with discrete data. I mean expression number 2. Here we consider cyclic component of the mathematical model 2, and this component carries information about the gas consumption process, and we present it in the form of expression number 3. In construction 3, there are segment cycles of the cyclic process, and they are determined through indicator functions, expressions number 4 and 5. The segmental cyclic structure, capital D is index small c, here is taken into account by a set of time counts. This form of the mathematical model 6 takes into account the rhythm of the cyclic process of gas consumption. Expression number 7. It's necessary to take into account, of course, changes in the amplitude of the load of segment cycles, which are caused by various climatic factors, for example, temperature, pressure, wind force, and others. And we denote these factors by a special vector P with index capital letter M. In model 4, we take into account its multiplicative components by using indicative functions and by using special scale coefficients of gas consumption amplitude, expressions number 8 and 9. Scale coefficients of gas consumption amplitude on each ith segment cycle are denoted by using expression number 10. For the climate indicator vector here, a fair ratio that takes into account the climatic parameters that affect the gas consumption in each segment cycle of the cycle process, namely expression number 11. So, figure 1. Here you can see a fragment of input implementation of cycling gas consumption process. Figure 2. Here you can see components of this process, particularly trend. Figure 2a and stochastic residue. Figure 2b. In figure 3 is presented the cyclic component, and we use this component for forecasting purposes. Figure 4. This figure shows only the maximum values of climatic indicators that affect the gas consumption process, especially temperature, atmospheric pressure, humidity, relative humidity of course, and the maximum value of the wind gust. Figure 5. Here you can see two approaches to forecast gas consumption values using different input data for training. We have used these approaches in our study. we apply two models and two sets of data to forecast gas consumption. Especially for the first approach, we use a neural network model of gradient boosting and a model based on decision trees for training. The obtained results you can see on the figure number 6. On the figure number 7 you can see the results of natural gas consumption forecasting by using the neural network model of gradient boosting and the model based on decision trees for training. The rho mean square error for the case of applying the gradient boosting model is larger than in the case of applying the model based on decision trees. And training the network based on the input data in the form of a cyclic component of the gas consumption process and forecasting on its basis showed that the rho mean square error is significantly lower than the others. Conclusions you can see in the slide number 14. So, in our paper, a gas consumption forecasting method was developed based on the application of gradient boosting machine learning methods and a method based on decision trees. It was found that the forecasting method based on the model of decision-making trees more accurately forms the forecast gas consumption values. Thank you very much for your attention.